Buffered aspirin is one good practical example of how you take a particular product so that it doesn't upset the pH of your stomach. The way that this works has to do with writing equilibrium reactions in which we have added to the system at equilibrium one of the products. A common example would be that if you have a weak acid in a system at equilibrium and then you add to that the conjugate base or the anion of that weak acid. What does that do? It shifts equilibrium back towards the undissociated acid and lowers the percent dissociation of the acid. But what you have in the solution is both the weak acid, this is their abbreviation for acetic acid or the acetate ion. So you have both the acetic acid and the acetate ion in the solution simultaneously. Conversely, if you have a base such as ammonia and the ammonium ion, you have both the base and its conjugate acid in the solution at the same time. And that's the whole idea behind buffers and the common ion effect. In your reading and past experience, I'm sure you've known that a buffer is something that when an acid or a base is added to it, the pH does not change. That's part of what a buffered aspirin might do, is keep the pH of your stomach from changing. It doesn't keep the pH neutral necessarily, it just keeps the pH at a certain value. And that value, as we'll learn later, depends on the weak acid and its conjugate base that are chosen for the buffer. So, depending on the buffer chosen, you can make a solution of any pH. And actually, this is related to the lab that you'll be doing on pKa, pH, and buffers. So here's one practical example. Calculate the pH, and I think you've already done something similar to this in previous problems, of acetic acid, 0.5 molar. Again, this is abbreviation for the acetate ion. Sorry for that. And 0.25 molar acetic acid, or sodium acetate. So why don't you pause the podcast right here and see if you can solve this last bullet point problem. Set it up before I go on to the next slide. That would be a good way to assess your understanding. How did you do? The pH. 0.5 molar acetic acid has a pH if you do the... Now notice this author has another letter for the ICE system to emphasize the fact that it's a good idea, actually essential, to write the reaction that is going on of the acetic acid ionizing into hydrogen ion and acetate ion. Also notice that a lot of times what scientists, chemists will do when writing acid-base equilibrium, in the case of the acid, we've really let the water off of the reaction and written a hydrogen ion instead of a hydronium ion. That's just a simplification. We know in reality that water is on the reactant side, that it isn't really hydrogen ion in the solution, it's really hydronium ion. But this is just a simpler way of writing the reaction, calculating the pH. Now if you think about it, what was the pH of this solution, or what would it be, if you only had 0.5 molar acetate ion and had not added the sodium acetate? You could have calculated that, and I think we did in a previous example. But in this problem, because we have a weak acid and its conjugate base, the way that a buffer works is that no matter if an acid is added to that solution or a base, you have both a weak acid and its conjugate present that will grab the hydrogen ions if an acid is added. Which of the two species would be grabbing the added hydrogen ions? Well, it would be the conjugate base, the acetate ion. And if you added a base, it would be the weak acid that would be saying, oh, I got this one. So again, when you have a buffer, you have a weak acid and its conjugate base. The important thing to remember is that in these kind of problems, when you add a strong acid or a strong base, keyword there is strong, then the first thing that you want to do is do the stoichiometry. All of that strong acid, because it is strong, or that strong base, will react with the weak acid or conjugate base, and then the equilibrium will be established. That's the simplest way to solve these problems, is first do the stoichiometry and then do the equilibrium. And in order to do that, it is the moles of the acid and the base added that are going to be reacting. So you've got to consider volume of the solution. You've got to figure out the moles of the weak acid and its conjugate. You've got to figure out the moles of acid or base added. So there's a number of different things to consider, but remember, it's moles that react, but when you're doing the ice table, it is the concentrations that go into the ice table, not the molarity. So we take that same buffer solution that we had a few moments ago, one where we have the weak acid, the acetic acid, and its conjugate base, the sodium acetate. Sodium, of course, is spectator ions. And now what we've dumped in is some base. Now, to simplify the problem, we're adding some base in the solid form so that if you added aqueous sodium hydroxide, then that would dilute the solution, and then that would involve one more step. So right now, we're going to assume there's no volume change and that we've added a small amount of base. What does it do? Well, first of all of that base will react. What will it react with? Well, it'll react with the acid. So you've got to do the stoichiometry first. So you've got initially 0.5 moles of acetic acid. You also have 0.01 moles of base added. So when they react, what you have is 0.45 moles of the acetic acid left over. But when the base neutralizes the acid, remember that what you're forming is more conjugate base. So now the acetate ion has increased from 0.25 molar to 0.6 molar. So you've got to do the stoichiometry. You've got to consider the change in concentration of both the weak acid and its conjugate base. Once you have the moles, then you calculate the concentration. For this problem, it's in 1 liter solution, so then our molarity and our moles are the same. So as you can see here, we've got the setup, we've got the equilibrium set up. If we know the equilibrium constant, 1.8 times 10 to the minus 5, then we can calculate the value of x. We can calculate the concentration of the acetate ion that is present at equilibrium after the reaction, and also the acetic acid, and then calculate the pH. When you do that, notice that the pH only now is 0.03 different than it was to begin with, without the added base. Now, if you had added 0.01 moles of sodium hydroxide, consider this, to pure water, then you'd have, to 1 liter of pure water, then you would have a 0.01 molar sodium hydroxide solution. And if you had a 0.01 molar sodium hydroxide solution, the pH of that solution would be 12. So what the buffer does is keeps the pH from changing. If you added the sodium hydroxide simply to acetic acid, you could also do the calculation. What is the pH? Pause it and do the calculations yourself. This actually is a little bit more than what you would do in sophomore chemistry. You would consider this a stoichiometry problem, but then it would be followed by a little bit of equilibrium. So calculate the answer. 3.05 instead of 4.47. So you can see the impact of a buffer on the pH. What this slide shows is an interesting take on another way to look at why the pH doesn't change. If you start with a general Ka expression and then solve it for the hydronium ion, or hydrogen ion in this case because they've simplified it, notice that you have the hydrogen ion equals Ka, and then you have a ratio of the weak acid and its conjugate base. So the hydrogen ion is related to this ratio. Now, if you do a little mathematics and take the negative log of both sides, well, the negative log of hydrogen ion or hydronium ion concentration is called the pH. And then when you take the negative log of this relationship, you have to apply some log rules. So you have the pH equals the negative log of Ka, which actually we will come to know that as the pKa. If you follow pH, pKa, pOH, etc. And so simplifying the equation and getting rid of the negative sign, you end up with the log of the conjugate over the acid. This equation here is called the Henderson-Hasselbalch equation up at the top here. So again, in general terms, a pH is equal to what we know as a pKa plus the log of the concentration of the base over the acid. The base being the conjugate and the acid being the weak acid. This works great whenever you have both a weak acid and its conjugate in the solution. Notice again, since we're talking about pH, which is a measure of the acidity, we're going to have a pKa, a subscript of A here, and we're going to have base over acid, log term. That'll become important when we derive the same equation for Kb. Perhaps you could try to do that yourself. Write the Kb for ammonia, and then follow through the steps from the previous slide and derive an equation so that it, instead of saying pH, it says pOH here equals the pKb plus. What does that equation look like? Bring the answer to that into class the next time we meet. This is a great equation. It simplifies it for a number of reasons. First of all, because notice that the only place where volume comes into play is in this ratio of the concentration of the acid over the conjugate base over the acid. And so you have a volume over a volume. So really the volume isn't important. So what you can actually use here is moles. Well, then you don't have to worry about the conversion of moles to molarity and back. This works great when the ratios are A, 1 to 1, and B, when you have an acid-base equilibrium where you have some of the weak acid and its conjugate or weak base and its conjugate in the solution. Awesome mathematics. Take this equation that we just have and redo the previous problem. Bring that work into class so that you can show me that you've figured out, wow, this is a much simpler process. Go use these moles, 0.26 and 0.49, and the Ka, 1.8 times 10 to the minus 5, and do the calculation. You'll find that this is so much easier. So here's another example. Again, you've got 0.75 moles of lactic acid, you've got 0.25 moles of sodium lactate. Again, lactic acid, the milk sugar that you might be familiar with if you're lactose intolerant especially. So you have what is the pH of a buffer solution? Well, if you know the concentrations of the weak acid and you know the concentration of the conjugate base, you can calculate the pH of the solution. So you start by taking the pKa, negative log of the equilibrium constant for the weak acid, and then you plug it into that equation and have the pH. Now, stop for a minute. And if you look at the next lab that's coming up, one of the things that you will be asked to do in this lab is find the Ka of an unknown acid experimentally. Well, you'll be able to do that pretty simply by measuring a known amount of the acid into the solution and recording the pH. And by doing a little bit of work with that, you'll be able to figure out its Ka. Knowing the Ka of your weak acid, I will say to you, I want you to make a buffer using your weak acid that has a pH of blank. So you'll have to figure out how much of the conjugate you want to have in your buffer, and you're going to make that conjugate base by neutralizing a certain fraction of the weak acid, your unknown weak acid. Confused? Try reading the lab that's coming up, and that'll help. Again, another sample problem. This time we have Kb. And so here's another approach. If you have Kb for a base, remember Kb is Kw divided by Ka. Right? Acid times base equals water. That makes sense. So the equilibrium constant, it also makes sense. Do the math using the Henderson-Hasselbalch equation, or the second one that you arrived, and calculate the pOH equals pKb instead, log of, and what did you find? Okay, so now we have this solution of ammonia and ammonium chloride, a base, a weak base, and its conjugate acid, and we add acid to it. Remember that a buffer can be made of a weak base and its conjugate acid. You cannot, by the way, make a buffer with a strong base and a strong acid combined, because all you'll have is salt water. And because the ions, the sodium ion and the chloride ions, do not form anything other than neutral solutions, you do not have a buffer when you mix a strong acid with a strong base. In this case, we've got a buffer solution, so that means that adding some acid, HCl, to this buffer should not change the pH of the solution. So do the calculation, pause the podcast, and verify before the next slide comes up that you can do this properly. Remember, the first step is to always do the stoichiometry. If you forget to do the stoichiometry, you'll end up with an incorrect pH and a complicated problem. Do the stoichiometry first. So here's the setup. Bring in your calculations for this problem to class the next time you have it. So calculate what is the pH of the solution after 1/10 of a mole of HCl is added to the buffer. Here's another problem for you to do. Do this on loose leaf again along with the other problems. Bring that into class. Calculate the pH. Remember, do the stoich first, then do the equilibrium. Always do stoich before equilibrium. A couple final points about buffers and buffering capacity. As you can imagine, you'll reach a point where you have used up all of the weak acid or its conjugate if you add too much acid or base to the system. And so the capacity of the buffer depends on how concentrated the solution is. And once that ratio is so depleted, either too much weak acid or too much conjugate base, then the pH will start to change. But as long as this ratio is pretty close to one another, you'll have a fairly decent capacity for your buffer to maintain a constant pH. Now, let me ask you this. If you add water to a buffer, what will happen to its pH? Mathematically, what will happen to the pH of a buffer if you dilute it? Bring that answer into class. So when you're doing problems, it's probably good to recognize that if you have an equal concentration of weak acid and its conjugate base, that is the situation where the pH equals the pKa. A good multiple choice type question, which would not require you to use a calculator. So the hydronium ion concentration equals the Ka. I can see that as a very easy non-calculator type question. Okay, so looking at this analysis problem, this is something similar to what you'll be asked to do in your lab. So you have an acid and you're asked to make a buffer that has a pH of 4.7 or 4.30, which weak acid will be the best? If you look at the equilibrium constants, it may not jump out at you, but right off the bat, the first step would be to take the negative log of these Kas. And if you know the negative log of the Kas, then you know that the one that is closest, where the pKa is closest to the pH, that would make the best buffer. Once we know and understand buffers, the stoichiometry of how the pH does not change with buffers, we're really ready to move into titrations, and that will be the subject of the next video.